welcome to come to this talk, which is about building a recommendation engine with Neo4j and Reco4PHP. First about me, so I'm Chris, coming from Belgium. I am a Neo4j and Elasticsearch consultant at Graph4. And today we're going to talk about, first, the challenge of building a recommendation engine. You will see that it's not just about recommending products that other people bought. There are a lot of other challenges than that. I'm going to make a quick introduction to Neo4j, which is a graph database. So who heard about Neo4j already? Who used it? Right, almost nobody. And then I'm going to introduce Reco4PHP, which is a recommendation engine skeleton atop Neo4j. It is a standalone library, so it is not tied to any framework. And we're going to make a quick demo about how to use it. The challenges. What are recommendations? So recommendations, you will find it every day on every website, mostly. So that can be news you should read, books you should buy, like Amazon, persons you may know, like Twitter, Facebook, which talk to attend. It is easy to recommend a talk to attend based on the topics of the talk, based on the text description, etc. Which service is best suited to handle a failure? So it is mostly in impact analysis. So when a server goes down, you can recommend which servers to start or other services. Finding the right candidates for medical proofs. So it is also recommendations, etc. So there are a lot of other use cases. There are three main types of recommendations. Content-based, so which is based on the features of the items. So for example, if I like a book which is a book about tragedy, you can recommend me other books about tragedy. Then there is the collaborative filtering, which is more about user interactions with the items. So if I like something, other people that like it could be potential way for finding new recommendations. If you heard about Netflix recommendation engines, they talk about matrix factorization. It is a kind of collaborative filtering. And then there is the knowledge-based, which is a more complex recommendation system, which is based on the user preference. It is mostly for books recommendations, for example, but we will talk about it. And then there is the hybrid approach, which is a combination of those recommendations. In terms of challenges, there are a couple of first business challenges, which is first finding items to recommend. So you will see that there are multiple ways we can find items. The second challenge is to serve the most relevant recommendation. So, for example, it doesn't make sense if I am buying a calendar to recommend me another calendar, right? And the last thing is measuring the quality of recommendations. So when you serve recommendations to user, you need to measure how users are liking it or not, what they are doing with it. And the fourth one is the time to market and cost of development. Building a recommendation engine takes time. And what I will present reduce the time for building it, but it is not only the building of the recommendation engine, but all the time after that, which is analyzing the recommendation engine. So imagine that you would build a feature people you may know on LinkedIn. Everybody knows LinkedIn, right? You need to find items to recommend. So First is you can find it through common contacts. If you link your Facebook account, you can find Facebook friends that you have in common with other people. Mobile email contacts in common. All contacts of your contacts. So, if you worked for the same company, if you studied as the same school, if you share the same interest, or if you live in the same city. But that's just the beginning, right? So we found it, but how do we recommend those recommendations to the user? If we have more contacts in common with someone, should it be more relevant to another one? So if I have 1,000 contacts, should it have a better score than someone with 500 contacts? If you live in the same city, or you worked for the same company, or you studied at the same school, does the size of it matters, right? So if I am working for IBM, there are a lot less of chance that I know someone in the company that if I am working for Coiffure or a small company. The same goes for schools. The same goes for city. I'm living in a small village, so there are a lot of more chance that I know the people in my village than if I would be living in Amsterdam, for example. What do we do, for example, with items that don't represent someone? For example, you will see on LinkedIn, you get, do you know info@laracon.eu, just because they found it in your email contacts, right? What should we do with people that you have an invitation pending, that you rejected, that you don't interact with the recommendation? So does it make sense to recommend you on LinkedIn always the same people, and you do nothing with those recommendations? So you need to find what the user also is not doing with the recommendation. And the worst thing is serving bad recommendation. So this was a tweet yesterday about Amazon. So you just bought a wallet. Do you want another wallet? This is how Amazon is working, right, with the recommendation. So maybe he wants a wallet for his wallet. So, but the user is really sensible to that. So the next time you see a recommendation, think about it. So you see, wow, that's pretty weird recommendation, that's bad. And you will feel bad about the site, and then maybe you will not buy to this site and find another site who will serve you real recommendation, better recommendation. And next come the technical challenges. The first one is the simplicity. So the theory behind the recommendation engines is already complex. So at the development side, we try to make it easy. The second one is performance. So you need to serve real-time recommendations. An example, if you go to the market, you buy a PlayStation, then you get your ticket. You take the other side, and you have a discount for a PlayStation. You are really disappointed. So it must be real-time. And the third one is flexibility, because when you build your first recommendation engine, or for other companies that this is their first recommendation engine, you will see that what you think is good for finding items is not always true. So for example, we worked for a jobs company in Spain. They wanted absolutely, the business people, to recommend people from Facebook contacts. And in fact, after analyzing, we found that people didn't like it at all. So you need to have a simple way to remove the Facebook contacts from the recommendation. Right. Neo4j. First, a disclaimer. These are not graphs, right? So if you type graph into Google, you will see a lot of images like this, but these are charts. Neo4j is a graph database. What is a graph? Graph has mainly two notions, which are nodes. Nodes is like a row entry in your MySQL database. Nodes can have labels. Labels is a way to group your nodes together. So you can compare it to a table name in MySQL, but it can have multiple labels. And a node with the label person, another node can have a label person male, another node can have a label person female. Neo4j is schemaless, so you don't have the constraints of schema for all your database. This is a good thing. Sometimes you need schema. There are features for having schema enforcement. But in 90% of the use cases, it is pretty good to have it. And node can have properties. Again, as I said, it is schemaless, so a node with the label person can have a property name. Another node with the label person can have 2 or 3 properties, etc. And nodes are connected by relationship. If you look at the relationship in the middle, it has a type, which defines the kind of relationship between the two nodes. It drives, in fact, your graph. So it adds semantic to your graph. You can compare the relationship to a join table in MySQL. It has a direction, and it can have 1 or more properties. Again, no schema, so one relationship can have 1, 2, or 3, or 15 properties. Doesn't matter. The graphs are everywhere in our life. So you have heard definitely of the Facebook graph, of the Twitter graph, and of the LinkedIn economic graph. But what we do in the life is a graph. So if somebody is tweeting about Twitter, about Laracon EU with the hashtag, another people is tweeting with the hashtag, so you can relate and find the implicit relationship between those two persons into a graph. And if you look at Neo4j, I will show you. Everybody can see? Yeah? Okay. It is easy to understand what is happening in your database. You don't have this kind of abstractions with joins. So you just look at your database. So this is the Neo4j browser dev tool. You just look at your database, and you can see, OK, I have a tweet. This person retweeted. This one also. This hashtag is tagging this tweet. This hashtag too. So if you look at also at this, it is really simple to understand. And it is also really simple to find things to recommend. So you have a database which is suited for recommendations. So if you take the hashtag, you say, OK, find me all the tweets. I just traverse, find me all the tweets, and I will recommend those persons to follow on Twitter or something. So it is easy to understand. The problem is that in a real Neo4j database, it will generally look like this. So it is not more easy to understand if you look at your database. So this is, for example, a representation of some activity on GitHub around a repository. So you need something to be able to query your database. So if you take SQL, it will not be possible. It is a complete other mechanism, a complete other way of thinking. This is why Neo4j developed a Cypher, which is the query language for graph database. There is a difference with SQL, is that Cypher is a declarative pattern language, so you describe what you want back from your database and not how to find it. So you will see, this is a query, for example. Match is like a select in SQL. And what is around inside parentheses is a node. What is inside square brackets are relationships. So you just say, OK, select, match, find me a node which has a label person with a name you, which attended this talk. And then I continue to traverse this graph. From the talk, find me other people that attended this talk. And I want also that the two persons lives in the same city. And of course, it cannot be me, because it doesn't make sense to recommend to me. And return it. So, easy. Well, it's relative, right? So, if we look at the graph here, let's say I want to find a node which has a Twitter account label and a property user screen name with my Twitter screen name. Return this node. Right. This is me. We found a node. Now we just expand. So we traverse this graph. And I say, OK, find me the tweet that this person tweeted. Oh, tweet. Right. I tweeted that. And then if you go further, so we can see here that there are mentions, there are replies. Take this one. Right, there are tags here. So we take the same query, and we just go further. No join, nothing. I want to find the tags of my tweet. Oh. All right, we get them. There are other things you can do with graphs, so this is cool. We have this tweet, we have this tag, we have users. If you think about graphs and you know about something, you know a bit about graph theory, there are this notion of paths. So you can find paths between two nodes, for example. So if I take me, and the Neo4j Twitter handle, I can find what is the shortest path between the two nodes. So if you look at this notion of shortest path, you can use a graph database to recommend routes to follow to recommend. Yeah. Whatever, when you need shortest path, for example, if you have a GPS application, you can use it. The star here is just telling the depth of relationships you want to go. So if you already had to do something like this, so traversing nested 2 depths, 3 depths, 4 depths with MySQL, you would have a query of 50, 60 lines. It is really difficult to do in MySQL. With Neo4j, it is just telling, OK, find me maximum paths with maximum 5 relationship. Also, I told you that relationship have a direction. It is true for writing time. So you need to specify direction at writing time. If you don't do it, Neo4j will choose one for you. So there will be always a direction at writing time. But when you query, you don't have to specify the direction. So you can query in both ways. So here, there are no arrows. Here. Or in one of both ways. There is no performance implication to query in one way or the other. There is performance implication when you don't specify it, but oh. Oh, yeah. Right. Makes sense. The shortest path between me and Neo4j is a tweet that Neo4j retweeted. So a tweet, so it makes sense. Right. Back to business. Do you have any questions before I continue? No. Now, why graphs? So I showed you Neo4j is very simple to understand, very simple to traverse, but it has a background thinking about it. First one is simplicity. So we talk about a recommendation engine. We did something simple to build a recommendation engine. A graph database is the most simple thing you will find. And maybe it's new to database now, but Neo4j is 10 years old, and graph theory is more than 300 years old. So it is crazy. Oh. And it is whiteboard friendly. So when you have a meeting, in fact, when you think you're just creating stuff like this, and in fact, what you are thinking is what is in your database. So no abstraction. So the features and relationships, so when we talk, for example, an item has this feature, or a user likes an item, are naturally represented in a graph. And the recommendation logic is really easy to express as a traversal. Like we saw, you just expand and traverse the graph to find what you want to find. And if you look at this, a simple graph, it is easy to recommend based on the both relationship or on the viewed relationships what item to recommend to one of those users based on what they liked and what they bought. Yeah, this is the query. So Sally bought an item. Who bought an item like her? What he bought? What are the products he bought, and recommend what not Sally bought already. Easy. The second thing Neo4j will help is performance. Neo4j, in theory, can traverse 4 million relationships per second per core. It is theory, so it is based on benchmark on machines that we cannot pay. So in my experience, you take the half, 2 million relationships per second per core. So if you have a 16 or 32 cores machine, you can make pretty good real-time recommendations. And relationships in Neo4j are first-class citizens. So if in any development right now, you have this notion of relationships, and it is maybe sometimes more important than your basic entities. In Neo4j, it is first-class citizen. There are no joins. And traversing a relationship is cheap. How to use Neo4j in PHP? I will not go to the basics of building the driver, etc. There are a lot of documentation on GitHub. There is a PHP driver. There are two object graphs mappers. So there is a doctrine graph mapper, which is the Neo4j PHP OGM, and there is an eloquent object graph mapper, which is developed by Abed, who's the next speaker, and it's on GitHub also. And the last one is pretty mature. The second one is 3 months old, so it is still in beta. So, but it is in active development. Now, we will talk about Reco4PHP, which is a skeleton. So it will not do something out of the box for you. You have to write still code. But it provides you a lot of base classes to help you. So the idea behind the Reco4PHP is that it's the standalone PHP library. It has an opinionated architecture, which is based on the experience we have about building recommendation engines in the real world. It is flexible, and it handles all the glue for you. So you even don't have to connect to Neo4j yourself. You just need to do your business logic. And the architecture is, you have an input, for example, a user to which you want to recommend item, or it can be a book to find similar items, for example. The discovery engines are the code you will write. In fact, it is just a query, a Cypher query, to say, OK, how do I need to find items to recommend? There are scores and score builders, because every way to recommend items doesn't have the same importance in your application. And there are blacklists and filters, which is more, for example, blacklist. I don't want to recommend items that I already bought, or you don't want to recommend people to follow that I am already following. The post processor is for modifying the score of the recommended item. And there are contexts, for example, how many recommendations you want, the Meteor, and in fact, it is more a key value in-memory store that you can use throughout the skeleton. For example, you don't want to recommend sunglasses when it is raining. There are decisions, so you need to write one way to recommend per engine. So every way to recommend an item will be a separated class. The discovery engine executes a graph traversal with a Cypher query, and items discovered multiple times are more relevant. So if I find an item based on the bought relationship, it will be one time, and if I find an item based on the viewed relationship, it will have 2 scores, which will be calculated. And this library helps to have the flexibility to build a recommendation engine atop Neo4j. I'm going to show you a demo. It is a demonstration based on a GitHub GitHub activity dataset. So GitHub provides an API to have the activity on GitHub, and it has, we synced it in Neo4j. The first thing to do is to recommend the library. And we have the model. So we have people, everybody knows GitHub, right? People's following people, people owning repositories, written in a language, people start repositories. And people are contributing to repositories also. How can we discover items? So in this demonstration, it will be finding repositories by the people you follow or are following you. This is an example of a discovery engine. So you say, OK, it extends a single discovery engine. You give it a name. And this is your query. So you just say, OK, the input is, for example, a GitHub user. What does it, who friends he follow? And the stars. And then this line. So I will strip off people that have more than 500 followers, for example. Repositories that have more than 500 stars. Why? If you are not starring Laravel, there is a good reason. So you know Laravel. So if you not star it, there is a reason. So why do we want to recommend you Laravel? And the problem with nodes with a lot of stars is that they will come back very often in the recommendations. And it adds noise to the recommendation. If I would recommend users, if you follow Taylor Otwell, your timeline will be always him. So he did that, he did that, he did that, he did that. So if you don't follow him, this is for a reason. So generally, it adds noise to recommendation. The second thing is that we're going to create a blacklist that I am the owner of. So it doesn't make sense to recommend me repositories that I am the owner. Again, you extend the base class. You just write your logic. So return me the repositories I own, and create a blacklist for it. So when you will find recommendations, it will be matched to the blacklist. And if it is in the blacklist, it will be dropped from the recommendation. And then post-process is I want to reward recommendations that are written in PHP. So it can happen on GitHub that you will have recommendations on a JS library, for example, but you want to, if you're a PHP developer, have more relevance on PHP repositories. Again, if you write your query to find, so find me repositories. So if the recommendation is written in this language, add 5 to the score. And then you need a way to assemble this. So 3 blocks. You define your discovery engine. You define your repositories, your blacklist, and you define your post-processors. And that's it. No. So this is my discovery engine. I added another one, so then it is not in the slide. So recommend me repositories again. So it is me. I contributed to this repo, who contributed also, and to which other repositories they contributed. And return me 100 of them. And then I put a new score. And this is what the database looks like. So it is a pretty big database. So here you find the repositories to which I contributed. And if you want to see the relationship also, and go right. So I contributed to this one, to this one, to this one, to this one. Right. And this is one of the repositories, and you can see people are watching it. There are branches, there are issues, etc. For calling the recommendation engines, you just define the connection to the database. So what is the host and the port? And you register the recommendation engine. So you can have multiple recommendation engines in the same application. You find the user. For example, we can find the author of Laravel. And you say, OK, engine, recommend me items for this input. So the input here will be passed to everything you have here. So it is passed in the method arguments of every classes, because you need to find the ID of the input. And now if we run it, here, we can see, OK, this is the item that is found. And this is why. So we have found there are 158 connections to the author of Laravel who are contributing also to the Symfony framework. And it is rewarded also because it is a PHP repository. The second recommendation is the Laravel framework. That is weird, right? Because he's the author of Laravel, and we will recommend him his own baby. Why? So this is what you get when you analyze the recommendation. So if you look at this, we're going to recommend the Laravel framework. What do you think you're going to do? Do you want to recommend him the framework or not? No. So you need to create a blacklist. And again, easy. You define your traversal. Find me the repositories to which I contribute. And it should be in the blacklist. And then you just, you just add it here. You run the same. And it is no more in the recommendation. Take the first one. Here. No. Twig. Sonata admin model. And debug. Before ending the talk, if you are interested in recommendation engines, you have to know that it is a complex topic. So I had to, when I joined my company 3 years ago, at the beginning I had to buy mathematics books again because I forgot almost everything that is in those ones. So the book on the left is a book about graph theory, but not that. And I think it should be in every engineer bookshelf. The second one is about algorithms, and this one is a base book about the recommender systems. Those are pretty three good books you will find on the market. Thank you. Questions?
Hello. I was wondering if there were any projects or types of apps out there at the moment using relational databases that you think would benefit from moving to a graph database?
If there is a benefit compared to MySQL, for example?
Yeah. If there's any applications that currently stick with a more traditional approach that would really benefit from moving to a graph.
There is a better performance. If you think what is the cost of a join in a MySQL database, you don't have to think about it. There is no joins in Neo4j. So every move, if you remove all the joins from MySQL, it will be pretty fast, right? So
would you say any time that you use a join in a MySQL database, you should consider moving to a graph database, perhaps?
Yeah, but not for everything, right? But if it is a critical part of your application, yes, I think you should move to a graph. Yeah.
Thank you.
Also, it is very common to have MySQL and Neo4j.
Thanks for the talk. My question is, someone over there mentioned like migrating across, like where graph databases would be useful if you currently use a relational database. Would there be any way to import? Because I assume many companies would have, start as in rows and rows of stuff in relational databases. Is there a way to import all that data into Neo4j?
Yeah, there are pretty multiple systems to import your data into Neo4j. The first one is it has a pretty fast CSV import system. So if you can export your database to CSV files, it has a mechanism to import very fast those CSV files. But then you best build synchronization systems. But for a first batch import, you can do it. Otherwise, you can create your own Cypher queries for writing to the system. Or you can go very deep and use the Java API. But the CSV system is very, very fast. So I think about 4 or 5 million rows per second for writing. So
thank you.
Hi. I had a question about the data as well. Obviously, a lot of more traditional e-commerce sites, for example, use the structured databases like MySQL. When you want to build a recommendation engine on one of those websites, would you say it would be the best approach to simply have a copy of all your data, of all your transactions, of everything that people have bought of your products in a graph database? Or would you say it would be better to completely migrate over to a graph database?
It depends on the cost of, what would cost you. In big enterprise, we don't see that a lot because they are mostly on Oracle or MySQL already with, you cannot change that like this. Mm-hmm. Startups are okay to have only one persistent system. But yeah, it depends a lot about the stage you are. But as I said, it is very common to have both database combined together. What we do a lot also is a combination with Elasticsearch, for example, where we have an Elasticsearch plugin that is calling Neo4j to boost the score of the search found in Elastic, for example, based on the user graph, for example. So it is very common to have 2 or 3 systems in your application stack.
And how complex would it be to keep those in sync? Because obviously your products will change over time.
I have the chance to work for mostly Java company. Neo4j is built in Java, so we can build Neo4j plugins. So the complexity of replications between Neo4j to Elastic, for example, costs nothing because it is handled by one of our plugins. And for MySQL to Neo4j, you have multiple systems. It depends also on the consistency policy you have. So if it should be transactional at all. Neo4j is fully transactional, so you can roll back a transaction. So it makes things secure for your synchronization. But yeah, it is code to write, right? So it has a cost, of course, but it's worth it, really, for recommendations.
All right, thank you very much.